Hey there, and welcome to The Explainer. Today we are going to tackle one of algebra's absolute best shortcuts, synthetic division. Seriously, if you've ever been stuck wrestling with those long, messy polynomial division problems, you are going to love this. Okay, let's be real for a second. Polynomial long division, it works, but wow is it slow. It's tedious, and there are just so many places to make one tiny little mistake that throws the whole thing off. It kind of feels like you're taking the scenic route through the mountains when there's a superhighway right there.
Well, what if I told you that superhighway actually exists? That's pretty much what synthetic division is. It's a clean, super fast technique that gets you the exact same answer, but in like a fraction of the time.
Okay, so let's get into it. Before we learn how to use this awesome tool, we've got to know when we're allowed to use it. And there's one really important rule you have to remember. So here's the deal. Synthetic division is a specialist. You can only break it out when you're dividing by a simple linear factor. That means it looks like x minus some number c. So things like x minus 5 or x plus 3, perfect candidates. But if you run into something with a higher power like x squared plus 1, you've got to stick with good old long division.
All right, now that we know when to use it, let's get into the how. I'll be honest, it looks a little weird the first time you see it, but I promise it's actually just a super simple, repeatable pattern. And this right here is the whole recipe. It's all about getting into a rhythm. You set everything up, bring that first number down, and then you just repeat this little two-step. Multiply, add, all the way across to the end. It's that simple pattern that makes it so incredibly fast. Now, once you have your row of numbers at the end, how do you turn that back into an answer? Well, that's where this key idea comes in. Your answer, the quotient, is always going to have a degree that's one less than the polynomial you started with. So if you started with an x cubed, your answer is going to start with an x squared. Simple as that.
All right, theory is one thing, but let's actually see this thing in action. We're going to walk through 3 examples, starting with a nice basic one and then working our way up to a couple of the trickier situations you might run into.
Okay, first up, a pretty standard problem. We're dividing x cubed plus 4x squared minus x minus 10 by x minus 2. Now, since our divisor is x minus 2, our magic number c is just positive 2. And here we go. Watch the process. We put our 2 out front and list the coefficients. 1, 4, -1, -10. First, just bring down that 1. Now, we start the rhythm. Multiply by 2, you get 2. Add the column, you get 6. Repeat. Multiply by 2, you get 12. Add the column, you get 11. One more time. Multiply by 2, you get 22. Add that final column, and we end up with 12. And that's it, we're done. So how do we read this? Well, those numbers at the bottom, the 1, 6, and 11, they become the coefficients for our answer. That gives us x squared plus 6x plus 11. And that very last number, that 12 on the end, that's our remainder. Okay, let's try another one. This time, we're dividing by x plus 3. Now, this is where a lot of people get tripped up. Remember, the format we're looking for is x minus c. So if we have x plus 3, you can think of that as x minus -3. That means our c value is actually -3. You got to watch that sign change. Let's see how that negative c value changes things. Bring down the 2. Now, -3 times 2 is -6. Add that to 1, we get -5. Then, -3 times -5, well, a negative times a negative is a positive, so that's positive 15. Add that to -13, we get 2. And for the last step, -3 times 2 is -6, which when we add it, gives us a 0. And seeing a 0 as your remainder, that is awesome news. It's like a little celebration at the end of the problem. It means our divisor, x plus 3, went in perfectly. It's a factor of the original polynomial. So our answer is just a nice, clean 2x squared minus 5x plus 2. All right, one last example. And this one showcases another really common trap. We're dividing x to the 4th minus 16. Do you see what's weird about it? The polynomial jumps straight from the x to the 4th term down to the constant. It's missing the x cubed, the x squared, and the x term. So here's the crucial move. For every single one of those missing powers, you have to put in a placeholder 0. See here? We have a coefficient for x to the 4th, which is 1. But then we need a 0 for x cubed, a 0 for x squared, and a 0 for x. Then we can put our -16. Once you've got those placeholders in, the process is exactly the same as always. And look at that, we get another 0 remainder. That confirms for us that x minus 2 is a factor, and it also tells us that x equals 2 is a root of that original polynomial. So our final answer is x cubed plus 2x squared plus 4x plus 8.
Okay, so you've seen how it works. You've seen a few tricky spots. Now let's just pause and really nail down the two biggest traps that people fall into. If you can remember to check for these two things every single time, you'll be golden. Just think about it for a second. From what we've just seen, what do you think is the single most common, easy-to-make error when you're doing synthetic division?
It's this one, for sure, messing up the sign of c. It is so tempting to see x plus 3 and just automatically use a positive 3. But you have to remember, the formula is x minus c, so you're really looking for the number that makes that divisor 0. The fastest way to remember? Just always flip the sign of the number you see.
And the other big one is forgetting those placeholder zeros. The whole system is built on these neat columns, where each column represents a power of x. If your polynomial skips a power, you have to hold its place with a 0 in your list of coefficients. So for something like x cubed plus 1, the coefficients are not 1, 1. They're 1, 0, 0, 1. Don't ever forget them.
So, okay, this is a fantastic trick for your algebra homework, but does it actually matter out there in the real world? Well, the answer is a big yes, and it shows up in a place you might never expect, computer science. And this is just so cool. There's a super efficient algorithm that computers use to evaluate polynomials called Horner's method. And guess what? At its heart, it is the exact same multiply then add rhythm that we just learned. Why? Because it's the fastest way to get the job done with the fewest possible calculations. So what you just learned isn't just a math shortcut, it's a fundamental piece of how we make computers fast.
And that just makes you wonder, right? Our entire digital world is built on finding the fastest, most elegant solutions to problems. Solutions that are very often powered by pure mathematics. So begs the question, what other math shortcuts are hiding in plain sight inside the technology you use every single day?